All right, let's continue. A little bit more, other questions we can ask about arithmetic in Zmod 12. Thinking a little bit more about multiplication, one of the crucial things is the idea of a multiplicative inverse, like 1 over 2 or 1 over 6 or 1 over 10 in the integers and the rational numbers. And an interesting thing is that with the integers, we expect hardly anything to have a multiplicative inverse. You have to go to rational numbers, fractions. But in mods, sometimes you can actually have a multiplicative inverse within just the mods, which is kind of more like an analog of the integers. It's interesting. But there's no guarantee. So Zmod 12, we're going to look and see if 3 has a multiplicative inverse. So we're going to look at, let's say, row 3. We could look at column 3 because it's all symmetrical. Let's look at 3. Okay, what does this mean? To have a multiplicative inverse, it means that 3x, we can solve 3x equals 1. Okay, now, again, just this less time, I'm going to bar these guys to indicate I'm really thinking of them as living in the Zmod 12, but I'll probably be lazy about that from now on. So I want to be able to solve this. Now, again, in integers, rational numbers, those are real numbers, it's 1/3, and that's how we write it down. But is there something in Zmod 12 that satisfies this? Well, that's easy to do on the table. You just look for a 1 in that row of 3s. This is all the 3 times x's it could ever possibly be. And we notice, there's no 1 here. There's not something else you can notice about all these numbers. They're all multiples of 3. Well, duh. But the thing is, if you look at this row, like the 5s, we'll do that in a second, that's not all obviously multiples of 5. They don't look like multiples of 5. So it's an interesting thing that in Zmod 12, the multiples of 3 actually look like ordinary multiples of 3. So that's an interesting coincidence. Okay. So the answer here is no. And so we can't solve 3x equals 1. There's no 1/3 within our universe of Zmod 12. So now what about 5? Here we're solving 5x equals 1. I'm going to drop the bars. Okay. And now we look at the row of 5s here, and we see, hey, there is a way to get a 1. In fact, 5 times 5 is equal to 1. So in other words, 5 multiplicative inverse, we wrote that as to the -1 power, like we would ordinarily with rational numbers. It's actually equal to itself. That's interesting. Now let's check and make sure that makes sense. 5 times 5 is 25 ordinarily. Reduce mod 12. Yeah, you subtract 24 and you get 1. So this is a very interesting fact, that 5, you can solve 5x equals 1, and it's actually 5 times 5 equals 1. It's another surprising equation. Okay, so we can take that further. We can start solving equations in general, or trying to solve equations in Zmod 12. We've already seen that when we restrict to the ordinary integers, there's lots of equations that don't have solutions. The conditions about GCDs and divisibility and things like that. So we shouldn't have a whole lot of preconceptions about this. We see with these very simple equations, 3x equals 1 and 5x equals 1, that sometimes they don't have solutions, sometimes they do, and we just want to be careful and go with it. Okay, so x plus 5 equals 2, that's back to the addition table. Okay, so again, we'll just look at the 5 row. Is there something that can be added to 5 to make 2? Absolutely. If you take, the claim is that x equals 9 works. Since 9 plus 5, and again, I'm going to be lazy and drop the bars. Now, if we did it as ordinary integers, it would be 14. Okay, and I'm just going to immediately reduce that and say, oh, 14, that's just an unreasonably, or a slightly more complicated name for the number 2. We're thinking of them as the same thing. Okay, so indeed, that has a solution, and it's the only solution. There's only, that's the only way to do that. Okay, so this is related to the fact that additive inverses worked really well. Solving purely additive equations in mods is really, really simple. That is predictable. Okay, now here's something that isn't totally predictable. 5 times x plus 9 equals 1. Okay, well first, let's see if we can figure out what the 5x would need to be. Okay, so 5x would need to be what? Something that when you add 9 to it, you get 1. Well, let's look at the 9 row over here, and we need to figure out, aha, there's where 1 appears, 9 plus 4. Oh yeah, because 9 plus 4 would ordinarily be 13. Reduce it mod 12, you get 1. Okay, so 5x, excuse me, would need to be 4. Okay, now you might say, obviously, we're done because the x would have to be 4/5, and that's not an integer. But remember, 5 worked pretty nicely up here. So now we go to the multiplication table. Okay, we'll get somewhat more sophisticated methods for this, and there are a lot more sophisticated things you can say about this, but this is not a bad way to do it for a small mod. 5x equals 4, so now we're going to go to that 5 row, and we're going to look for a 4. Aha! Okay, this seems to claim that 5 times 8 is congruent to 4. Yeah, 5 times 8 is 40, subtract a 36, and so you're going to get 4. Okay, so x is in fact 8. And we can write it all together as 5 times, oops, that looks a little weird. Since 5 times 8 plus 9 is equal to 1. You could do it all in one fell swoop. 5 times 8 plus 9 is 49, then finally reduce by 12. Subtract 48, in other words, and you get 1. Okay, a few more. 2x equals 7. Okay, so that's just a purely multiplicative equation. But notice the 2's here, like we noticed with the 3's, the multiples of 2 in this mod actually look like honest multiples of 2. That was not true with 5, and that's one reason why it was possible for the 5 row to have a 1 in it. But these things, these are all honest multiples of 2, and in particular 7 is not appearing there. Okay, so this is impossible. Okay, and 7x equals 2. Well, we might think that's just going to be equally impossible, but let's look at the 7 row. Okay, the 7 row, that is more interesting. Okay, that doesn't seem to have quite as predictable pattern, and in particular, a 2 does appear right here. Aha, right, 7 times 2 is 14. Reduce it mod 12, you get 2. Okay, so here, x equals 2, and it's unique. There's only one solution. Okay, so sometimes with multiplicative stuff it's impossible. Sometimes you get solutions, just like multiplicative inverses. Multiplicative inverses is the key example really, where you're trying to solve ax equals 1. Here is a little more interesting. It's like ax equals b. Okay, and I think just one more. X squared equals 1. Ooh, let's see about, this is really thinking about square roots. Okay, well let's see. If you want to look at squares, you might want to pause a second and think where squares appear on the multiplication table. It's an interesting question. Okay, they appear on the diagonal. These are just all the squares. Just anything times itself. And what you notice is 0, 1, 4, 9, 4, 1, 0, 1, 4, 9, 4, 1. So that tells you that only certain numbers are squares mod 12. And in fact, they happen to be very similar to just the one-digit square. They are the one-digit squares. It's a bit of a coincidence here, I have to say. But in particular, we can look at what x's multiply together to be 1. So there's actually, surprisingly enough, there's 4 solutions. We might think, oh, it's just plus or minus 1. We get 1. We do get 11, which is congruent to minus 1. So those are the ones that aren't too surprising. But we also get 5. Oh, we knew that. That was up here. And we get 7. Because 7 times 7 is 49. Reduce that and you get 1. Okay. So a lot of interesting explorations with mods, some unexpected surprises, some hints that we've got a lot more work to do in terms of multiplication than addition. And the great thing is that when you're staring at a multiplication table, you can do it all just by sort of brute force, guess, and check.